When we talk about a logarithm is the inverse of an exponential. So, for instance, if I have the log base a of x is equal to y, I can switch that over to an exponential by taking the base and raising it to the answer and setting it equal to what you were taking the log of. A little bit easier to see when you plug numbers in there. All right, so let's look at this one. Log base 2 of 3 is equal to 8. We're going to take the base, raise it to the answer, and it's going to equal what we were taking the log of. All right, so we could say 2 to the 3 is equal to 8. Now, a couple things about logs you'll notice is that you cannot take the log of a negative number, or of 0. So whatever you're taking the log of has got to be positive. Your base always has to be positive, and it can't be equal to 1. All right, so let's practice switching back and forth here. So let's switch from logarithmic form to exponential form, just like we did a second ago. So to do that, we're going to take the base to the answer is equal to what I was taking the log of. Now, going the opposite way is a little bit harder. So again, it helps to just have a pattern. So let's take this pattern that we had right here, and we're just going to reverse it. So a to the y equals x will be log base a of x is equal to y. So notice that for a, we're just going to plug in 4. And then for x, we're going to plug in 16. And for y, we're going to plug in 2. And then we can rewrite that as a log. All right, so let's look at some examples. All right, we've got the log base 2 of 32. So to begin with, I'm going to put an x over here for what this is equal to, and I'm going to switch it from its logarithmic form to its exponential form. So I'll have 2 to the x equals 32. Now, you may know off the top of your head what power to raise 2 to get 32, but if not, anytime we're solving an exponential equation, we want to get our bases the same so that we can set our exponents equal to each other. So I want to rewrite 32 as a power of 2. So 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So it's 2 to the 5th. Now, once our bases are the same, we can set our exponents equal to each other, and so x is equal to 5. All right, here are some more. So we're going to say 3 to the x is equal to 27. So again, you may know what that value is immediately, but if not, you can get your bases the same. So 27 can be written as 3 cubed. Once your bases are the same, you can set your exponents equal to each other, and x is equal to 3. All right, look at the next one. So for this one, we're going to say 4 to the x is equal to 2. So 4 to the x is equal to 2. You may not know what this one is off the top of your head. So again, let's get our bases the same. Let's rewrite 4 as 2 squared. And remember, when you have a power raised to a power, you multiply. So that would be 2 to the 2x equals 1. So now my bases are the same. I can set my exponents equal to each other. And I'll divide both sides by 2 and get x equals 1/2. And that makes sense once we see it, because 4 to the 1/2 would be the square root of 4, which is 2. All right, here's another one. 10 to the x is equal to 1 over 100. So again, I need to get my bases the same. So I'm going to rewrite 100 with a base of 10. That'd be 10 squared. And then to move it across the division bar, to move it from the denominator to the numerator, I use the negative exponent. And then once my bases are the same, I set my exponents equal to each other, and I'll get x equals -2. Now, there are some properties of logarithms that we can use as well. If you take the log of 1, that answer is going to be 0. So for this next one, we've got the log base 3 of 1. It doesn't matter what our base is, the log of 1 is always going to be 0. And you can see that here if we switched it to exponential form. All right, the next one says that if you take the log of a and the base is the same, then your answer is going to be 1. So here's an example of that. If we say 2 to the x equals 2, when our bases are already the same, this is 2 to the first power, so x would have to be equal to 1. So again, here, that is that same property right there. All right, exponents and logarithms are inverses of each other. So if you have a logarithm and you're taking the log of an exponential and they have the same base, they'll undo each other and just leave you with x, because inverses undo each other and take you back to what you started with. Same idea here. If I have an exponential raised to a logarithmic and their bases are the same, they'll undo each other and take me back to what I started with. And then the last one says that if you have log base a of x equals log base a of y, well, obviously log a equals log base a, so that means x has to equal y. And here's an example of that. If I have the log base 2 of x is equal to the log base 2 of 3, then x would have to equal 3. Now, if you see a log that does not have a base, that is the common logarithm, and it is understood to be a base of 10. So when you see log of 3, that is the log base 10 of 3. And let's throw those into our calculator and see what we come up with. So grab your calculator if you would please. I'm going to use a graphing calculator. All right, so your log button is right here. So I'm going to do log and then 3, and that would be the common log, the base 10 log. And then the next one was 2 times the log of 2.5, and again that log had a common base of 10. So whether they write the base of 10 or not, if there's no base, it's 10. Even if they write the base of 10, that is the common log, and that is the log button that is on our calculator. All right, if we want to graph a logarithmic, first off, I've got g of x is equal to the log base 2 of x. I'd rather work with it as an exponential, so I'm going to switch it over to its exponential form. Remember that g of x is the same thing as y, so that would be 2 to the y equals x in its exponential form. So you can see it's going to be easier to plug in numbers for y than for x. So I'm going to go through here and just plug in some values for y to get my ordered pairs, and then I'm going to plot those ordered pairs, and this is the graph that I come up with for my logarithmic. Now, there are 2 landmarks that we're going to use for a logarithmic. That's going to be an x-intercept of 1 and a vertical asymptote at 0. Now, we said that exponentials and logarithmics were inverses of each other, so they should reflect in the line y equals x. Also, you'll notice that this is x equals 2 to the y, and this is y equals 2 to the x. All right, so if I graph y equals 2 to the x, remember that there were 2 landmarks for our exponential functions in our last video, and that was that we would have a y-intercept at 1 and a horizontal asymptote at 0. So y-intercept at 1, horizontal asymptote at 0. And then if this was a positive value, then our graph, if it was a value greater than 1 or our exponent was a positive x, then that was going to be an increasing function. So again, here's the line y equals x, and you can see that the exponential and the logarithmic do reflect in that line. You'll also notice we had already in our previous video defined the domain and the range for the exponential, but you'll notice the domain of the exponential is the range of the logarithmic, and the range of the exponential is the domain of the logarithmic, because again, x and y just switch places. There is a special logarithmic function called the natural log, just like there was a natural exponential function. So if we had y equals e to the x as the natural exponential, if we switch x and y, because remember that's what we do for inverses, I would have e to the y equals x, and if I switch that from its exponential form to its logarithmic form, then I would get y is equal to the log base e of x. So y is equal to the log base e of x. Now, mathematicians abbreviate log base e as ln. So if you see ln2, that literally means the log base e of 2. All right, then these are the same properties that we had just a second ago. The only thing that they've done is instead of having log base a, we've got log base e. So log base e, or ln, you can again see the natural log of 1 is going to be 0. When your base and your exponential are the same, then you're going to get 1. If you're taking the log of an exponential and your bases are the same, they'll drop each other out and just leave you with x. If you're taking an exponential and raising it to the logarithmic, then they will undo each other since the bases are the same and just give you x as well. And then, as we said, if the log and the base are the same and the log and the base are the same, then what we're taking the log of would have to be the same as well. Now, you also have an ln button on your calculator, so let's try these, ln2 and ln-1. All right, so here's your ln button right here. Again, when I click it, it lights up in red. So ln2 and then ln-1. Now, when I put in ln-1, I'm going to get an error message. Do you know why that is? It helps us a little bit here. They give us a clue. It says error non-real answer. What did we say the domain was for a logarithmic? What can you take the log of? You can only take the log of numbers greater than 0. So if you happen to forget that and you try to take the log of a negative number, or you try to take the log of 0, your calculator will make sure you remember that's not possible.